to the cloud. All right. So welcome. This is the last class before the last class in which I want to cover material, and the actual last class is tomorrow. And what I'd like to do is turn it into a consultation hour. I don't want to use that to answer questions about the homework because those were already supposedly turned in, and you had opportunity to discuss those in the office hours. But more questions about the material. If you have any questions, about the whole semester, there might be something related to nonlinear dynamics 1 as well, if you still have that. So I'll just be here available online for the duration of the class tomorrow, from 10:15 to 12, or 10:15 to whatever, 11:45, right? So feel free to just dial in or join in, and even just to listen if you have a question. And then I believe I've sent out already the exam scheduling for everybody, and you have instructions. Again, the only crucial point that you should be able to share your screen and walk us through your solution. And if need be, then you should be able to somehow write at least elementary scribbles, not extended detailed equations or something. But I try to keep that to a minimum. And I designated officially 30 minutes for each exam. I anticipate finishing earlier than that, but this is the maximum. And in the unlikely case of an overflow, if we are cutting into your time, then you will be in the waiting room. Of course, you get extra time, but I don't think it happened last year at all. So we'll be done normally in less than 30 minutes. Okay. Any questions about the logistics of the exam? I think everybody has received their own designated time slot. And there's one more homework that I believe is due tomorrow. Okay. So if there's no question, I just want to finish this material that I've been covering, which is spectral submanifolds, a type of invariant manifold family that's very relevant to dynamical model reduction in dynamical systems. And unlike the rest of the material, this material is very contemporary. So there's actually people in this class too who have been participating in the development. I may get to that point if I have time in the end to show some recent developments. But itself, the theory itself, the first rigorous results on these types of invariant manifolds, unlike everything else you've seen in this class, came out in the early 2000s. So it's relatively new, right? In core courses, we don't necessarily, certainly not in dynamical systems, react that fast. But even those results were by and large not used at all. And the people who were working on these results were writing further papers to, develop generalizations and tweaks on them, but they did not enter the applied community. And just give you some pointers to papers that actually made the translations, and the spreading of these ideas is ongoing, and the applications to actual physical mechanical problems. This was a little example. I wouldn't call this a mechanical problem, but just to give you an idea, even I think we did this paper in 2016, just 4 years ago. This was news because there was no such example in which you could actually work out what these manifolds are and show that the smoothness results are in fact optimal. You cannot do better than what's stated. So yeah, probably need my coffee at some point. But this is kind of a toy example just to remind you for the general context in which these results work. The most general current available context is almost this, except that if I take out the forcing, then this would even work in infinite dimensions. So this could be actually an evolutionary formulation of a partial differential equation. But then you would have more conditions, slightly more conditions on this linear operator. And this would have to be some bounded functions. So the spectrum of this has to be well behaved. In finite dimensions, generally speaking, when you have a spectrum that's bounded away from criticality in the sense that, whatever is required, bounded away from zero in this case, or imaginary parts, or real part is non-zero. As long as it's bounded away, which just requires simply that there will not be a single eigenvalue being on the boundary of validity of the theory, then you're fine. In infinite dimensions, that's not enough. You can have a spectrum that technically is not singular in the sense that there's no eigenvalue that would be zero from the point of view of whether zero is to be avoided, or it would have, there's no eigenvalue that would have zero real part. However, you can have an accumulation of eigenvalues there. So they can get infinitely close to that. And that, in fact, negatively impacts on the invertibility of the operator. So that is not allowed in cases like this. And it does happen, and basically something like that happens also with the heat equation. And that's for these reasons, these operators, these partial differential equations governed by such operators admit a perfectly nice flow in forward time, but not in backward time. So the issues come up when you try to invert them, or at least with the heat equation, you can actually run it for a web and it blows up on you. So that's the only difference, that you have to be a bit more stringent with the spectrum of A. So it's not enough just to the eigenvalues to have the right real parts, but other than that, actually it does extend to infinite dimensions. So the broadest finite dimensional context in which right now the theory is rigorously known is this, that you have a linear part, you have an equilibrium fixed point at X, you have a linear part, nonlinear part, and you may add then some small forcing to that. And that forcing may have a finite number of frequencies, K. That can be anything, but still has to be a finite number. These are R times differentiable functions, and R does play a role here. I don't want to go through all the conditions, but you have to have a negative spectrum in terms of negative real parts. And this is how you order the eigenvalues. And then you can ask if any combination of eigenspaces that you put together to obtain an eigenspace, spectral subspace, as we call it, can be continued in the nonlinear system or not. And in this extended setting, when you also have forcing, not just the autonomous part, there's an absolute spectral quotient, which I talked about last time, which you can associate with E, and that would be the smallest real part in the full spectrum of A, divided by the largest real part in the spectrum of the restriction of A to this E, right? So this is a characteristic of the linear space, of the linear spectral subspace that you wish to continue and hope to continue in the nonlinear system. Why would you want to do that? Because especially when this is all built out of the slowest, I don't know, L directions or M directions, then we have discussed that's your perfect reduced order model candidate, the dynamics on that, because everything else gets attracted to that, and you have a guaranteed low dimensional model. But it doesn't live on a subspace. You have to work to get that invariant manifold, right? So this was pretty much the picture, that you have some spectral subspace, then you construct the spectral submanifold, this all for zero forcing, and then you turn on the forcing. And under appropriate non-resonance conditions, what you hope to achieve is a continuation of the structure that you see here. What you see here is not just this point, but you have to then consider this in the extended phase space even before you turned on the forcing, so that adds K frequencies. So what appears here as a dot is in fact an invariant K-dimensional torus. And what appears as a cup-shaped surface there, you have to kind of shift that along the torus at each and every point to get a bundle of those surfaces. So you essentially have a cylindrical surface before perturbation. That would be the spectral submanifold associated with the torus. But there's no coupling between the torus and this dynamics at this point. When you turn on the forcing, the two gets coupled, but the good news is that this structure persists. So there will be a nearby torus, very close, order epsilon close, and attached to that, there will be such a spectral submanifold. And this little example, and unique, was just highlighting that this would be your linear part, then you're adding the nonlinear part, and then finally adding the epsilon term. And it's a longer formula, but it's in the paper that you can explicitly show that indeed attached to a torus, there's such a spectral submanifold. You can explicitly compute, and you can show that anything else that might be tangent to the same spectral subspace, there will be infinitely many such players, they do not reach the differentiability of this one. And this was just simply plotting the results. So what I wanted to do today is just bring this closer to reality in the context of mechanical systems. And that's where it does apply, you know, in any nonlinear system, but it's, since the focus of my group and several people working on this has been mechanical systems in this context, then we've been looking at applications to mechanical systems. So in the context of an n degree of freedom then forced weakly nonlinear mechanical system, the equation of motion is not a first order equation to begin with, but rather it's a second order equation. So the standard form, which I'm sure you've seen, is a mass matrix times some generalized coordinate, second derivative thereof. That's positions and angles. And damping matrix times the generalized velocity, the stiffness matrix times the generalized positions again. And in this context, we can be fairly general. We don't have to assume actually much about the nonlinearities. They are dependent on positions and velocities. They don't have to depend on anything else. Oh, no, sorry, they can depend on all these. They are at this point not allowed to depend on time. If everything also has a periodic time dependence and you're able to verify the properties that we have for the Poincare map of this system, that also works. But that's not immediately available to you. You would have to do that numerically. So this is the ODE formulation, but there's an equivalent map formulation. And the map can be the Poincare map of a time periodic system from which you then perturb. So this part can be replaced by a time periodic dynamical system, but you will still need to know that it has a fixed point at q equals 0, and you would still, which is a periodic orbit, right, for the full system. And you would still need to know its spectral properties in a fairly detailed manner. And that's not just an algebraic calculation as it would be here, right? Because here you would be calculating eigenvalues, eigenvectors to establish the same thing for a map that you don't know explicitly, because the map is a Poincare map of a time periodic system is not so easy. I mean, it requires detailed flow case theory for the fixed point. Anyway, so that's also possible for parametrically forced systems that have time dependence already before they have external forcing. But I'm not looking at that. I'm looking at an autonomous mechanical system plus external forcing, and under several frequencies, we can have a quasi-periodic forcing function here. I have the epsilon here, which for reasons that I have explained before, I think, namely that, of course, if you don't care about, and many don't, if you don't care about mathematical validity, I don't have to write that there. I'm just saying I can do this for any forcing, but that's not true, because if you pick some huge forcing, then the impact of that forcing drives you away from the equilibrium point. When you're so far away from the equilibrium point that you don't even see it, so to speak, then it doesn't make any more sense to split the dynamical system into these two parts, because this is suggestive of somehow the fact that this part, the nonlinearity, is smaller than the rest. But no, when you're away from the equilibrium point, the nonlinearity may be easier, larger than the rest. You may be completely wiping out any sign of the original linear dynamics, okay? That's why we formally have that epsilon there to point out the range of validity of these arguments, okay? So M is a mass matrix, it's symmetric. K is a stiffness matrix, symmetric. C is a damping matrix, it's symmetric. Let's assume that M is positive definite, as it would make sense for a mechanical system. And again, for the physics, we want C and K to be positive definite. Structural damping hypothesis is not necessarily true physically, but it's very convenient. And for lack of a better idea, people just tend to use that in modeling. It's debatable to begin with whether viscous damping is the right damping model for a steel structure, right? And probably not really, right? And there's evidence to the contrary. Nevertheless, it does give you a nice exponentially decaying profile, so people use it for modeling purposes anyway. And also the other assumption that people often use is that the damping matrix is written as a linear combination. So this is Rayleigh damping or structural damping. It's a linear combination of the stiffness matrix and the mass matrix, because it's up to you how you model it. But if you model it this way, then the same transformation that puts the mechanical system, this part, to a modal basis, to eigenmodes and decouples them, will do the same in the presence of damping as well. If you don't make this hypothesis, it's not going to happen. So you're not going to be able to work with decoupled modal equations. But this does that for you. So for epsilon equals 0, you have a linear system for which the ansatz for its solution is this. So an exponential, excuse me, exponential term e to the lambda t times the corresponding amplitude. That's how we always try to solve linear systems. Amplitude is non-zero. You plug that in, and this is, if you have a vibration course, then you've seen this, that this leads to a second order equation for lambda. It's a second order characteristic equation, completely analogous to the theory of linear systems when they are in a first order form. Here could rewrite that, but then I lose the sparsity and I lose the convenience of having just a single equation. So I want to do it in this setting. These are the eigenvalues, lambda 1, lambda n, and I rank them, in growing order. In fact, this should be lambda 2n, sorry, it runs up to lambda 2n, not lambda n. Because this is an n degree of freedom problem, and for each mode you have 2 eigenvalues, either complex conjugates of each other, or say 2 real eigenvalues. Let me get into that later. So this is actually 2n here, right? And I put them and order them in a way as I did before, is that the weakest one, the least stable eigenvalue, is the closest to the origin, and I have a decreasing order. So this mimics what we had before for the SSM setting, but now in the setting of second order systems. So the corresponding eigensolutions or linear normal modes in mechanics, we look for them in this form, and we can show that that's the form to look for them. So some exponential, whereby in the exponent you have the real part of the eigenvalue, the jth eigenvalue times t, and a harmonic term whose frequency is the imaginary part of the eigenvalue, plus you have some phase shift. Because normally you would have sines and cosines. Sine imaginary part lambda jt times something times cosine imaginary part lambda jt times something. But if you take something else, that is, but if you play with the two something, the something and the something else, and normalize them, pull out a common factor, then you can view that sum of a sine and cosine using the summation formula for not sum, the sine formula for the sum of two angles, and introduce a phase here. And this term then multiplies what we call the mode shape. And that will be the eigenvector that you get from this calculation. Okay, so an individual linear normal mode, as we say in linear mechanical systems, would be this, with this type of a decay, right? This type of a harmonic oscillation with a phase shift, and with this mode shape, linear mode shape. Now, an actual solution is a linear combination of these. And if the imaginary part happens to be 0 for a given mode, then, which means that the corresponding eigenvalue is just the real part, then we call that mode overdamped, and it decays exponentially without oscillations. If that's not the case, but we also have an imaginary part, we call that underdamped. So that also means oscillations, right? Typically that's what you see, that the lower modes tend to oscillate, and you go higher, then the damping at some point might cause some of the modes to be overdamped, and then they decay straight without oscillations. So what we then do in mechanics normally to set this problem up cleanly, and that's where this assumption of structural damping becomes handy, is that we transfer the system to modal coordinates. That's the analog of diagonalizing first order systems. So for first order systems, at this point, we would pass to eigen coordinates, which would be given by the eigenvectors. Here we pass to these mode shapes, right? So you put them together in a matrix, modal matrix, if you will. These are columns, the mode shapes. So this is you have an n by n matrix, And you write your current generalized coordinates as this m by n matrix times the new coordinates, the modal coordinates that you want to transfer to. So it's a linear transformation. And when you execute that transformation, how do you do that? You just plug it into this mechanical system here, right? Then what you end up getting in modal coordinates is this second order weakly nonlinear oscillator form. So in the ith modal coordinate, you will have xi double dot for the inertial term. The mass is normalized away to 1 because this is, you would have an mi here, but I have this divided already by that. And then you get this damping factor multiplying xi dot, and it's traditional to write this damping as the natural frequency whose squared would appear here times 2 times whatever is left, because that will become advantageous when you actually want to express the eigenvalues. So this damping, modal damping factor, when that's larger than 1, that turns out to correspond to the overdamped case. In that case, this linear part for this particular ith mode would have 2 real eigenvalues, okay, damped. But if this damping factor is less than 1, that's the underdamped case. And when you work out the characteristic equation for the second order system, in that range, you would then get a pair of purely imaginary eigenvalues. And the real part is just omega I, and the imaginary part is just omega I, and the real part is related to this factor. The nonlinearity also needs to be transformed, but again, that's doable. You simply substitute for what you see here in Q, and you do the decoupling and then divide by mi, the individual mass that you would get here in that transformation. That gives you little si. And then finally, in the same equation, there was forcing. So at some point in the coordinates transformation, this also appears. And that just basically the projection of the forcing onto the modal coordinates. That's what comes out to be. So you take the forcing and project it down to the ith mode, which is basically to the ith column here, okay? And then what you end up having here, you get after, dividing by this mi. So it's a normalized forcing, but it's nevertheless small. So the point is that this is the natural frequency, and this is the modal damping factor. And this is the modal forcing, and these are the nonlinearities. Now, these are the terms. Often this is just a sine or cosine function that does the forcing independently on each mode. So the coupling would come in from the nonlinearities here, right? If there's coupling mode. This was just a paper that we wrote. Mattia is a student in my group still, although it's finishing up very soon. And he has a great paper with some great results, from which I'm not using the results, but I'm using, because those are about something else, but I'm using this figure. And the figure, we kind of wanted to have a figure in which we wanted to show all the possible things that can happen when you take modes like this. And remember, a linear system will have n of these. And you add nonlinearity and you start forcing. So the linear system, what you see here, this is the forcing frequency. And if all you do is just harmonic forcing and you don't add the nonlinearities, then a linear system, as we learn in vibrations, if these are the frequencies, the natural frequencies of that system, then the system's response under pure forcing and still no nonlinearities would be symmetric bumps around these points. And typically this is what you get. So this is the response curve, and it typically goes down. If the system is not forced, or the system is not damped, rather, then these are, in fact, forcing frequencies at which you would have a resonance between the linear system and the forcing, the natural frequency and the forcing, and therefore the oscillations that actually grow to infinity. And outside those, the two frequencies, namely the forcing frequency and the system's natural oscillation, would not really communicate with each other and would not really lock onto a periodic motion, but you would get quasi-periodic motions. So it might, if the question is, what is the amplitude of the periodic response, then here and here, outside these spikes, you wouldn't have any. But once you add damping, then damping helps the synchronization of the system onto periodic orbits and also removes the possibility of infinitely large response at resonances. So what you end up getting instead is peaks. And also in between those resonances, as I'm showing here, I mean, look at these individual points. Those are all periodic responses of the linear system. That means there is a periodic orbit with that amplitude here. So if I take that particular forcing frequency, then this is the response of the system, that periodic response. And these peaks happen at resonances of the linear system. Now, what this figure shows here is what happens when you add nonlinearity to the picture. So what happens, let's just assume that this is still not nonlinear. It's just a linear, say, harmonic forcing, because that's the standard that people apply to interrogate a modal response. However, assume some general nonlinearity here. That general nonlinearity will distort these symmetric peaks in the response curve and make them either hardening, as you see them here, or softening. Whenever you see such a response curve, that's a strong, that asymmetric response curve, that's a very strong sign of nonlinearity of the system. And this is typical in applications and experiments. I think we talked about cases like this, that whenever you also see an overhang over other branches, that actually means that at that frequency, you have coexisting periodic responses. One with this frequency, which is stable, then you go and you get another periodic orbit, which is then unstable, and the third one is stable again. This is, remember, when this happens, and it typically does happen in any experiment, this leads to the phenomenon of hysteresis. That if you do an upward, we discussed that, I think, in nonlinear dynamics 1 when we're talking about bifurcations, that you do an upward interrogation of the system, you're sweeping the frequencies upwards, and you get this periodic response, which is stable, and that's what you see. And then in your experiment, you're actually here, that particular branch becomes unstable. So you will be jumping here and follow that branch. The way you would live through that in an experiment, that, okay, I had a periodic response, and that is a sensitive dependence, because if I increase the forcing frequency just a bit, then I continue in this branch. And then you would be happy, but except that you discover that. But when you come backwards and you're changing the forcing frequency backwards, then lo and behold, you don't jump back there, but rather you would discover this new branch here, until that one loses its stability, at which point you would jump to the upper branch and continue from there. So this particular curve here that you would experimentally find, very typically, this is called the hysteresis curve. And this is entirely due to, as we discussed in nonlinear dynamics 1, to 2 saddle node bifurcations that happen to those periodic responses. One is here, because see, it turns back, and the other one is there, it turns back. So just to relate what happens here, this is a saddle node bifurcation of periodic orbits. So it happens at the level of the Poincare map of the dynamical system. Now that doesn't have to happen in this direction, it can also happen in that direction. And then that's sort of the reverse hysteresis, is that in a downward sweep, you would jump here, and then when you go upwards, then you would jump there, if I do it correctly. So these are the 2 basic phenomena. These curves have what people call backbone curves. They are theoretical centerpieces, along which, for any given forcing amplitude, you get the largest peak. Because one thing about nonlinearity also is that, as I was discussing the linear systems, once you normalize these curves, once you normalize the response with the forcing amplitude that you're putting in, it's the same curve, it's universal. So if on this axis I show the response amplitude normalized by the forcing amplitude, then we learn in vibrations that it doesn't matter what forcing amplitude I employ, as long as I normalize the response by that, I get the exact same curves, because the forced linear response is proportional to the input forcing level. That is no longer the case when you add nonlinearities. Then for each and every curve, even though you normalize with the forcing frequency, for each and every forcing level, you get a different curve. So ultimately, you end up getting a family of curves, all right? And these are already normalized, but even then, they differ from each other. And as you increase the nonlinearity, the more they start differing from low levels. So that's why you see a whole family of curves. And the one which is faded would be for the response amplitude for any given mode for a higher level of forcing, and the one which is more strongly visible, which is the more strongly red or darker red, would be a lower amplitude. So there's always a whole family of these. So that explains one aspect of this. The other aspect is that if you then take those families and connect their peaks, then you will be getting something which is called the backbone curve, which actually has a conservative limit, which means that in the limit of vanishing forcing, it will, or vanishing damping, excuse me, it will limit on yet another curve. And if that curve, and also have to turn on the forcing for that. So that curve would be the conservative limit of the backbone curve, which turns out to label a family of periodic orbits in the corresponding conservative Hamiltonian system. It's called the conservative backbone curve. But in practice, you don't see that because you always have some damping. If you turn the system off here, by the way, if you had this forcing frequency here that gave you the maximal amplitude, and all of a sudden you stopped forcing the system, then lots of experiments and numerics show that you very nicely come up down here along that curve. So what does that mean? Or another way of seeing that is that this actually reflects the dynamics along a particular SSM, a particular spectral submanifold that was born out of a spectral or modal subspace associated with this peak of the linear system, okay? Because the linear system had a resonance there, which means that for this particular forcing frequency, there was a linearized frequency that was in resonance with that. And when you look at the two-dimensional modal subspace, say it was an oscillation, oscillatory mode, then that defined a two-dimensional invariant plane in the linear system on which these were the motions with constant amplitudes. You put in some damping and a nonlinearity, it will take this peak and deform it into something like that. But that thing is still corresponding, or now it's corresponding to a perturbation of the linear subspace, the corresponding spectral submanifold. And that manifests itself in the fact that if you then turn on the forcing at the peak and you still have the damping, then the spectral submanifold nicely guides you down to zero. So basically, this is you're somewhere in this surface. You're moving near that surface, actually on the forcing, if you will, the surface itself moves. But if you all of a sudden you take away the forcing, then the surface freezes in whatever position it was, and all of a sudden becomes a static autonomous invariant manifold for you, on which the dynamics now, since there's no forcing, is purely damped. So it will be spiraling towards the origin, right? Which means that your amplitude is shrinking. And that's very nicely shown even in experiments, that it's coming down like that. So this is in some sense a cross-section of the SSM, which lives in a very high dimensional phase space. And I would be hard pressed to show it as a two-dimensional manifold, but imagine this line as crossing through in the radial direction, and you're checking your distance from the origin. And this is how it would be decreased. So there's a lot of stuff in this diagram because I've been explaining this for a while, but just that served just to explain what the various curves here are based on their color. Now, not only can you get various colors for these different types of behaviors that now I think I have covered all of them. I talked about the force-damped backbone curve being the center of these force diagrams. I talked about the conservative limit of that. And I talked about the fact that you have different forcing amplitudes. And I have talked about two possible scenarios already that you would see experimentally, one of them being the hardening and the other one being the case of a softening spring. So when you see this forward overhang in an experiment, that's always the sign of a hardening spring. The other one is the softening spring. But this is what we typically see, in elementary vibrations classes. But actually, there can be a general combination. There can be a combination of the two phenomena. So this would be a softening hardening case where you start out softening and then you become hardening. Even more interestingly, let's first see, there could be modes along which you in principle have a backbone curve, but it's not being activated. You don't see much action along them, at least not for the forcing levels that you have employed. Okay. And it can also happen that maybe you don't see much action at the immediate level, but you see what we call a subharmonic response there. So it is generated by, so your forcing amplitude is here, okay? Sorry, your forcing frequency is here, and that doesn't happen to be in resonance with the current, with any of the natural frequencies, okay? But it happens to be in resonance with some higher amplitude or higher amplitude periodic orbits that live near that natural frequency. In other words, if you take a look at the conservative limit of those backbone curves, then those were filled with zero damping and zero forcing with periodic orbits of the conservative system. Now, it may happen that I'm looking at the first mode now, that you have currently a forcing frequency that you have added to the conservative system, which is not in, so that this is not in resonance with your forcing frequency might be somewhere here, 3 times as big as this is. But as you go up along that level, along that family of periodic orbits, and hence you keep changing the periods, one of them may hit a resonance with that forcing, okay? With that forcing. So you not with your current forcing, well, sorry, no, your current forcing is this, sorry, so suppose you're here. So there was an orbit family that is reacting to your current forcing, because when you go up that tree, then there will be a resonance between that orbit and this forcing frequency. So make a long story short, that will happen here. How am I explaining this? No, I'm mixing the two. So if it happens here, that means my current forcing frequency. That's for sure. But I'm pointing at the wrong thing. There was no resonance here. So at this current forcing frequency, there was no primary natural frequency activated, but along that branch of that primary frequency, there are all of a sudden regions that are in resonance with my current level of forcing, so they have become alive. And to make a long story short, if I did a linear analysis, I just would have seen this and nothing else. And I would have had no idea that detached from that, there's something what's currently being called, or actually for a while has been called an isola. An isola is an isolated response island. And what's particularly interesting about this is that if you use a numerical continuation code, then you will most likely miss it, a code applied to your differential equation that tracks periodic orbits, because numerical continuation codes tend to follow branches of existing solutions. So it would nicely march along and get this one, but will not get this one. Also, it's easy for that reason to miss it experimentally, because for your given level of forcing, you are out of the primary resonance and say, okay, I'm in, in calm waters. That's it. Maybe I increase my forcing level a little bit, okay? But I'm not seeing anything, so I'm not gonna focus on this region. It turns out that you really have to apply a fairly high forcing level to see this. And it can be a nasty surprise in an experimental situation, because you don't expect in this regime, if you don't know about this one, you don't expect an alternative response, another stable, steady state, and your structure might just get a large perturbation, and unexpectedly, then instead of going back to what you thought was the only stable position for its oscillation, you get stuck in there. And when it, maybe one large oscillation amplitude is not a big deal, but if it does sustained oscillations there, then it's pretty heavy load on the material because it wasn't planned for such high oscillations. That can also happen when these isolas can also occur by way of a bifurcation. They can detach from peaks, or they can merge with existing peaks, right? So that's another phenomenon. So you may have no sign at the linear level, but an isola, or you may have actually a sign of a bump at the linear level, even at the nonlinear level, but there additionally to that, there can be an isola here. Anyway, so these are all the possible phenomena that can happen in a nonlinear oscillatory system. And nonlinear vibration analysis or nonlinear modal analysis targets these and wants to predict them or identify them from existing nonlinear oscillatory models. Why am I mentioning all this? Because I did use the term spectral submanifolds maybe once, but why are they relevant? They're very relevant because it turns out that all these behaviors, these are all, any point on this curve is a periodic orbit, right? A non-trivial periodic orbit. So these all live on spectral submanifolds. They all live on lower dimensional models or surfaces that become alive, they become forced at the appropriate frequencies. So what are those appropriate frequencies? Well, the SSM corresponds to an eigenspace over which it's a graph for a while, right? Whatever the linearized frequency of that eigenspace was, if it responds to the forcing that I apply, because it's either equal to the forcing or it's some lower order multiple of the forcing, okay? Then all of a sudden the spectral submanifold becomes energetically distinguished. All of a sudden you are able to create non-trivial behavior on it, periodic orbits and all that. So that's the reason why there's huge potential for capturing all these things just by constructing spectral manifolds, spectral submanifolds corresponding to these natural frequencies, so that the kinds of spectral submanifolds you're interested in this analysis is the ones that are in linear resonance. The linear approximation is in resonance with the particular forcing frequency. So to set that up just formally, to see that for this system, the results are applicable, I put it in first order form now, just for conceptual reasons. I didn't do that at the beginning. Now it's very sparse, so I'm not paying a price for introducing a first order form. I would pay a price if I did this right at the beginning. I would destroy the sparsity, but this remains now sparse. I'm just rewriting the modal equations. So X, I take the modal coordinates, which I had here as xi. I put them together with their velocities. Yi will be the corresponding modal velocities, and I have a variable which is zi. This will be just a relevant two-dimensional modal variable whose first component is the modal displacement, and the second component is the corresponding modal velocity. So then I just do the usual transformation that I would do to bring this second order linear system to first order linear system. And then I add the nonlinearities. So xi dot equals yi, and yi dot is the -2 times all the damping times xi dot, but that's just yi, minus omega I squared xi. So this is the linear part now. This is the az part. And then I identify the nonlinear part. The nonlinear part is sparse in the first equation. There isn't any because that's just a defining equation, xy dot equals yi of the velocity. So everything appears here because this is xi double dot. So all the nonlinearities appear here. And I write x dot, but I have to express x dot in terms of the yi's. So I should actually do that. I do that. So this is xy, and the same here. So this nonlinear term then actually takes this modal equation and couples it to the rest of the modal equations, because in modal coordinates everything decouples at linear order, but the nonlinear terms do couple all the modes. And then you have the forcing here, which may or may not depend on, let's just assume that it doesn't depend on positions and velocities, the purely harmonic, then it will have these omega ITs, right, that I had here, which I individually define as phases. So I introduce a phase vector, which is just omega IT. So for that reason, if I introduce such a phase vector, then I add that as an additional variable. So the corresponding equation will be phi dot equals omega. We did this before. So you basically have a core of the system, which is n-dimensional, and then you're adding k equations, which correspond to these phases in the forcing. You further enlarge it. In fact, this is, yeah, I mean, this is not n-dimensional, sorry, this is 2 n-dimensional. Individually, you have n of these and n of these. So all together, this is 2 n-dimensional. The index runs from 1 to n, but you have 2 equations. And then you have k equations. So this is now in a first order form, to which I just wrote it in this form because it's exactly in the form for which we had a quasi-periodic SSM theorem. So that result applies here. And one can then reasonably hope that we can individually continue these 2-dimensional spectral subspaces, which I now call modal subspaces. These are 2-dimensional spectral subspaces into their nonlinear counterparts. If that damping coefficient is larger than 1, then that means that that particular, if zeta j is larger than 1, then that particular modal subspace is overdamped, which means that within that subspace, you have a node type dynamics. You will have some faster decay, and which I'm showing here, I guess, and you will have slower decay. And that's the particular unit that you would like to continue under the nonlinear system. So what will that be? Well, it sort of perturbs into something that, again, it's a graph over this one for small values of the nonlinearity and the forcing. But then you also have forcing, so you have to cross it, this construct with the k-dimensional torus. And this is precisely what I discussed before, right? This is for the overdamped mode. If it's underdamped, that particular mode, and again, normally you may well have a combination. Some of the modes for some j will be overdamped, some will be underdamped. Then this linear modal dynamics takes place on a plane which has a stable spiral, right? Stable focus. And again, what you're doing is you're interested in extending this into a nonlinear spectral submanifold in which maybe you just have simple decay, but maybe not, because if you just have on that simple decay, that means that then you're decaying down to the continuation of this fixed point, but that continuation now involves, includes k frequencies. So you would be somewhere here, for instance, which means there's only one response, periodic orbit, for instance, and nothing else. And to that, you come down or go up depending where your perturbation is. If the forcing was quasi-periodic, then this would not be a periodic orbit, but a quasi-periodic torus. So overall, your SSM dynamics would be just boring because either you come down in amplitude or go up in amplitude. This corresponds to that simple spiraling, right? But look at these cases here. For that given forcing amplitude, say it's just periodic with one frequency, you have one stable state, you have one unstable state, and yet then you have another stable state. So what we know then is that on this SSM, after I've added the nonlinearities and the forcing, life will be not as boring as I'm showing here, but the Poincare map will see several fixed points coexisting. Okay, it will see maybe a stable one, but it also might see, you know, two unstable. So wait, see, well, this is a possibility that I'm showing here, I guess, the two unstable ones and stable ones. But here, for instance, in this case, this would be stable, unstable, stable. So you would have two stable ones and one unstable one. So this would actually be an unstable one here, two stable ones there, right? Something like that. So that all happens on the spectral manifold. So if I can compute them efficiently, then I can predict what's going to happen here. It turns out even without doing simulation. because you can introduce polar coordinates on these in which the dynamics is so simple that you can read off the actual first, at least at leading order, the actual periodic orbits, because they will be fixed points. So that's a bit technical, that part, so I'm not going to go into that, but at least I wanted to give you a sense why these are relevant and what their footprint is in response curves. So they contain basically all this dynamics information individually. So if you go after them and find them approximately, then you can construct this curve without having ever to do an actual frequency sweep, okay? And therefore you can also make predictions for experiments. The geometry of what happened. Oh, by the way, any questions so far? I realize I'm probably going fast, but I at this point, I just wanted to give you an idea of what's going on, because this is the, there are papers being written about this and growing material, but at least to give you a sense what these are good for and give you a sense that they are very relevant, even predicting outcomes in experiments. And if I have enough time, I'll get to that, show you some pictures. But any questions on at least the big picture questions on these? That's an excuse for me to sip some coffee.
Okay. Yes, if I may. Am I audible?
Yeah, please go ahead.
Okay, thank you very much. So I encountered the nonlinear vibration diagrams before back in Budapest, and there we did with this other method, I think that was not done in your paper, the Poincaré small parameter method. We explored these amplitude responses. Mm-hmm. And there I only recall, I don't recall the method exactly, but I only recall seeing the softening and the hardening one, and also softening, hardening together maybe. But the isolas and the subharmonic responses and also the inactive ones, they were not touched. Is that a limitation of the method, or was it just our well, not so rigorous approach?
Right. I mean, there are very small parameters involved in various perturbation methods, and they only work because there are a priori scalings introduced. Let's scale the forcing with this amplitude, let's scale the displacement. And for that particular scaling, you introduce an ansatz, and in that, the domain of validity of that scaling, you will get results, okay? But that's not the full story. For instance, if you mentioned the isola is basically not related to what you're perturbing from with classic perturbation methods, because classic perturbation methods look at the linear frequency there. And they ask the question, do I see a resonance between that and the forcing? No, then we move on. So there's nothing to perturb from, right? So they're not able to deal with out of the blue branches that are coming from a high order nonlinear resonance. But so that's the reason that those methods have limitations. You would, I mean, there are tricky scalings that, and well, not just, I mean, you need a version of the Melnikov. In fact, this paper was all about that. So using classic perturbation methods to try to, for instance, predict this using small parameters and you name it, and the types of machinery that you're familiar with, but it wasn't perturbing from the base state, which is the linear system, but it was perturbing from the set of nonlinear periodic orbits, which is generally unknown to us in the conservative limit. But you can build a perturbation theory among those and try to predict which one survives. And this is this theory. This was the first time that Melnikov's method, which is always classical low dimensional method, was applied in this setting. In fact, the prior versions of the Melnikov method do not apply. So this was a new Melnikov method developed in this paper that first time ever enabled the actual detection of these things directly, right? So what I'm saying is that, yeah, that's absolutely in order, because this is, again, contemporary material to find these with more advanced methods.
Mm-hmm. Right, thank you. And another one, I was really wondering, I like the very intuitive approach of the subharmonic and the isola responses. That's kind of easy to get, but sometimes if I get a perturbation on the wrong place, I go into a field that is unknown for me and I resonate there. But what's the thing with the inactive responses? That is kind of hard for me to wrap my engineering brain around, because there was a resonance in the linear case, right? And that just vanishes.
So the reason why you can have an inactive response is that in order for you to have and the end result is that each and every point is a periodic orbit, right? Whatever happens, wherever we are in the system, whatever the force, each and every point of this diagram is a periodic orbit. Now, to have a periodic orbit means that you have to have a balance of work put in and work taken out, because you have to get back to the exact same point in the phase space. All right. Now, that means that you have to have a dynamic balance between the forcing and the damping. And in some case, and all that in the context of what the available nonlinear conservative dynamics allows you, because you basically, what happens here is that let's take away the forcing, let's take away from the damping. You have a conservative system, say Hamiltonian system, that has families of periodic orbits along these backbone curves, okay? Now, if you apply small forcing and small damping, you have the potential to preserve some of those periodic orbits in the force damped case, perturb them. Many of them will be destroyed, but some of them will survive. The Melnikov method, in fact, tells you which one survives. And the Melnikov method, when you work out actually the details, is nothing else but the leading order energy balance. So you integrate at leading order, the input by the forcing, the work performed by your external forcing along a conservative periodic orbit. And you also integrate, or you also figure out at leading order, the energy that you dissipate along that orbit due to damping. And you only have a chance to have an active response. Now, to answer your question, to have an actual dot there that represents the periodic orbit if they are equal. And it may happen that you have a branch, and for the forcing frequencies that you have it explored, they are not equal, because just somehow on that particular periodic orbit, given the nonlinear circumstances, the two effects, damping and forcing, have no chance to balance each other, okay? Because they have to do that balancing act over a skeleton, which is the limit of the, which is the limiting periodic orbit of the conservative nonlinear system. So that's where the conservative system comes in. And you know, these two are competing with each other, damping and forcing, and they say, I want to keep balance. And the conservative system comes in and says, not so fast. You can only play that game along the framework that I'm giving you in that regime, because you also have to, since both of them are small, you have to play that game along that particular, whatever twisted conservative periodic orbit that I'm giving you over there, right? And not all modes will then give you a response. And this is really true. We verified numerically, we didn't get anything along this branch. Is that really true? Yeah, and you don't get. It's not that you don't get anything, you do get the perturbation of the trivial state always, right? So within the SMS, you will have that base point, which is still there, that survives. But if you check the rest of the SSM, I said SMS, so it's SSM, spectral submanifold, then you get just decay down to that, okay? Again, it might happen that if you then start looking, and that's what would happen here. However, when you're willing to increase your forcing level, then it may happen that all of a sudden at some higher amplitudes, the Melnikov method starts telling you that, you know what, you're trying to get this done in the right place, because at this point, the constellation is great. The types of periodic orbits, the work you're doing with that level of forcing, high level of forcing, and the damping, you have a chance to balance those out. And then all of a sudden, an isola pops out. But if you don't go high enough, you just see this mode as inactive, meaning that it's not that it's not oscillating, but it's oscillating, but it doesn't seem to be showing a resonant type response, right? At this point, you get the same type of oscillation that you would get here if I cover everything up and you don't see this part. So that's what I mean by inactive. And it can also happen that inactivity just persists way up. And because just the particular nature of the nonlinearity, that for all we know, for this particular scaling that we're imposing here, epsilon forcing and so on, it just not responds that way. It does respond periodically. It's not that there's no periodic response, but the backbone curve doesn't get activated in a nonlinear case. What does that mean? It means that the backbone curve in the conservative limit had all these periodic orbits in the conservative orbit, and all of them are destroyed. except for one here, which is actually not even out of those, but it's perturbs out of the equilibrium point. Okay. Again, is that valid for the full phase space? No, because this type of analysis and this type of reasoning that I'm describing here is valid under this scaling. So that also limits the range of the forcing, that there's an epsilon there. Right? So in that sense, this is a local analysis, and one can always get surprises way up there. But in what I'm trying to state here is results that are mathematically defendable and rigorous and can be deduced, right? And which is not the full story. However, it's a very relevant domain, because when you do materials testing, I mentioned that before, somebody, you know, has an airplane and people are doing, say, you know, for preventive purposes to prevent damage and diagnose material problems, cracks or whatever on the airplane, they do material testing. They're not going to go there with a sledgehammer, right, to destroy, or because that wouldn't go down well with the airline and the pilots. So at the best, what they're allowed to do is just sort of minimally invasive testing, right, small amplitudes, and those are the diagrams that people generate, right? So it is relevant. You don't want to destroy the structure just in order to prevent it from getting destroyed, right? That's one way of preventing a structure to get destroyed. I destroy it myself and don't let it to self-destroy, right? That's not the idea, but basically just excite and get as much information from non-invasive techniques or minimally invasive techniques. That's why actually, you know, some propose not to have these shakers at all, but rather use other forms of completely non-invasive testing, like X-rays and things like that, right? Okay, anything else?
Only if I do not disturb really the lecture. I have one last question.
Yeah.
Oh, thank you very much, sir. This one is the far-fetched one. So you mentioned the testing and trying to find out so critical responses from real systems, and in those systems, that's also a large question, and this is a reason why this frequency and amplitude response plots are very useful in engineering, is that we can combine these things after Fourier analysis. So you just take an incoming signal, because you won't always have pure harmonics acting on your system, and then take it apart, and you can just apply, because your system was linear. But this is a non-linear system. Is there any research going in the direction of combining these things? That seems very, very hard, but
that's a very good point. I mean, what you're asking is a harder thing to do, because it will no longer be a one-dimensional response curve, right? But it will be more a graph. So even when you have two frequencies, then it's already, that's going to be a two-dimensional surface, basically, as a function of two frequencies. And people have been trying to do that, but the complexity of the response just grows suddenly. And all of a sudden, on this one, you could have local bifurcation, self-intersecting curves, and yeah, that does exist. Now, to decompose, I'm sure that I'm really not a vibration expert. In structural dynamics, I'm sure people have to do with stochastic forcing. We have to do with highly transient forcing that are by no means harmonic. I'm sure they have ways to do that. I'm not familiar with that. I'm more familiar with the mechanical engineering practice, in which usually you say, okay, in this particular part of the engine, I will have a main frequency excitation because there's that machine part that has that particular motion, and I'm interested in the response to that, right? But even then, I know that people try to model the effect of the road noise with whatever white noise, and that's more of a, there are techniques for that I'm not familiar with, stochastic linearization and things but are fundamentally, everything as far as I can tell is linear. So there are hacks for linear systems, but for nonlinear systems, we're even just trying to figure out what happens on this, periodic forcing. And that is not to say that there aren't, results for quasi-periodic forcing. But they, after a while, they get super messy with these add-ons to these diagrams back and forth connecting. So what you're asking is certainly relevant, but it's very challenging from this point of view.
Okay, thank you very much.
Sure. So sorry that I cannot be more specific, but that's also something that is not a developed area yet, and that I think people are trying things what to do. I mean, I've seen attempts, but usually for very low dimensional oscillators, typically a 1 degree of freedom oscillator forced by 2 different frequencies. So let's move on just to cover the rest. So this would be, again, the other form of a spectral subspace. And then when you force this, then it perturbs into a 2-dimensional manifold. And on that manifold, you can have several motions coexisting. I mean, just draw a curve here and you see how many. When this is more exotic, you can have even more motions coexisting, right? At which point it tells you that you need to have a good high order approximation for the spectral submanifold to capture all this. I just wanted to recall briefly the geometry. What it means is that, so I think it's not easy to see, and that's the disadvantage of having, just walking you through things that I have drawn before, but please forgive me that I tried. Most of the course was not like this, but I haven't yet figured out a way to present this very briefly. I guess that's part of the reason I need to figure that out. So that means that I have to spend more time on it than I would say spend on center manifolds. But also the reason I'm spending more time, because actually I think it's a whole lot more relevant at this point for contemporary model reduction. So anyway, so suppose that in this linear system, here's the origin, and here's a representation of your slowest spectral subspace, E1. Again, that's a 2-dimensional player in mechanical systems. So when I draw a line, that's actually a 2-dimensional plane. Then let's assume that E2 is somewhat faster. Again, it's a 2-dimensional plane, either underdamped or overdamped. And so that has 2 arrows because that's a bit faster. And E3 would be the fastest. Actually, I should have the 3 arrows on that one, but I only see 2. So let me add 1. So these individually can be continued under the non-resonance condition. So see, this was my slowest spectral subspace. Then just to illustrate what happens in the phase space, that will have a nonlinear continuation, this green entity here, the WE1 T0. Since I have forcing, it's not attached to an equilibrium, but it's attached to a torus here. This represents a torus with K frequencies, right? If it's just one frequency forcing, single frequency forcing, then think of this as a periodic orbit. So think of this then, what you see here is for the Poincare map. Why don't we stay in that framework? That if it's just one frequency forcing, and this is a fixed point of the Poincare map, as I'm showing it now. And out of that are sticking these 2-dimensional planes. This is the slowest, so it has a slow SSM continuation, this green one, VW1. Then here's the one who has an intermediate decay speed based on its linearization. It's somewhat faster, but still not too fast. That's WE2, again attached to the torus or periodic orbit. And the fastest one is here, E3. And of course, there are many others. So if you will, you can take E3 to be just the rest all crumbed together, right? Because that's the advantage of the theory, that for each and every one of these, you can put several together. So maybe E3 is just the rest, several all the remaining modes. But again, they will have their own nonlinear continuation, assuming that we have the non-resonance conditions that we normally assume. Then what's the meaning of this? If you then take a general initial condition in the phase space, then very quickly, and you're close enough so that this whole story matters, and you haven't destroyed the structure to begin with, this is your initial condition, then these modes will very quickly, these are the fastest decaying modes, so they will die out very quickly along your trajectory until you get close to this large SSM that I have actually constructed over the span of E1 and E2, because that's also possible. If you take that to be E, then it has its own nonlinear continuation, as long as it's not in resonance with the rest. So not only will you have these individual blue, green, and red continuations, but you can take the slowest guy, and then you can take the next one in line, and that's a 4-dimensional spectral subspace, and continue that into a nonlinear object. And that's what I'm showing here, which then will also contain the individual nonlinear continuations, right? So these two curves are within that large spectral submanifold. All right, so make a long story short, you start with this initial condition, you start dying out, you got very close to this larger spectral submanifold. You're so close that these components have essentially died off. They are now exponentially small. What do you do then? You're close enough to the spectral submanifold, so you start picking up the dynamics within the spectral submanifold. When you're within the spectral manifold, then all of a sudden this becomes the fast decaying direction, and the other one, the slowest, is the slow direction. So this component then starts in your next time scale decaying fast, relatively speaking. I mean, not as fast as these were, but now, relatively speaking to the green one, this is decaying fast until it sort of dies out, which then puts you very close to the green curve. It will not put you on the green curve because that would violate uniqueness of solutions. You started off this large spectral, started off all of these spectral submanifolds, so you will never actually intersect them, because at that point you would have loss of uniqueness of solutions. But once you get close to them, you pick up their dynamics. I mean, think about the foliation of stable manifolds that we discussed before. You're close enough to a stable manifold, you start mimicking, you're hitting the appropriate fibers, and they guide you, and you start mimicking what the trajectories do on the manifold. So that's why you die off, and then you die off, and you get close to the slowest one. So there's a hierarchy of timescales, and depending on how many of these you're interested in capturing, you can decide whether you just need a two-dimensional spectral subspace, because ultimately you just want the final asymptotics, or you also want transients because you're building a control circuit for which it's important to capture also some of those secondary timescales. Then you go with a two-dimensional one. Or if you want the rest, then you start peeling off some of the directions that you have included here, and you start building higher and higher spectral submanifolds. Now, it turns out that to capture most of what's going on here in these resonances, unless they are not playing together with each other, so unless one of the natural frequencies says the second one is not in resonance with the first one, then you're perfectly okay just going after individual spectral submanifolds here. Okay, well, but which ones? Well, the ones which tend to be in resonance with the forcing, because again, if they become relevant for this value of the forcing under normal circumstances, unless you have a nonlinear resonance, this first mode is not reacting to that. It doesn't care because it's not in resonance with the forcing, therefore no transfer of energy is possible between it. It's not ready to develop sustained oscillations just because you're forcing it at this frequency, right? You need a resonance for substantially unidirectional energy transfer to happen between the forcing and that. So it's not taking up any. It starts reacting when you actually shift that to here or nearby. Then the slowest SSM starts mattering. Likewise, if you're tinkering around with your forcing frequency, which you keep changing on the second SMS, which would be generally corresponding to the second natural frequency, then that SSM is ready to do business with you. So all of a sudden, this one, which was this one, is becoming important. So you're able to then create energy balance between the former, in the shadows of the former conservative periodic orbits that were here. You're able to create now, following, in their footsteps, a balance between forcing and damping. And you're able to develop non-trivial response along this curve. And those would be these guys, these dots, and so on for the rest. And therefore, then you're depending, if you want to understand what happens there locally, then you can construct these individual spectral submanifolds using a Taylor expansion, which sometimes is easier said than done because you then have to get your hands dirty, you have to write an algorithm, but it's fundamentally doable without any simulation. And then you can do a normal form on those SSMs, which will put you in a polar coordinate setting. As I said, you can explicitly look for these non-trivial orbits without still any numerical simulation. So you can actually construct that response diagram very well. So this is what I was trying to say here, I guess, with with this summary that the most important case in practice is when you have, perhaps maybe for reasons of tradition or reasons of simplicity, when your forcing has a single frequency, not more. And then what's of interest is to predict the forced periodic response and not just quasi-periodic response in general. And then the strategy is to reduce to a spectral submanifold, which is a perturbation of the spectral subspace on which you're activating periodic response. The simplest way of activating a particular SSM is to your forcing frequency is, say, on 1-1 resonance with the natural frequency, which is the imaginary part of the eigenvalue that corresponded to that SSM. So maybe this was, this is the equilibrium point. This was when one of the linear modal subspaces whose natural frequency down here is in all of a sudden in resonance with your forcing. Then there's a chance that nearby, when you then move away from that particular resonance frequency, so your forcing frequency is not exactly that natural frequency, but something close. However, then you will find nonlinear periodic orbits of the conservative limit, which are then actually in resonance with that. That means you have a chance to preserve them. You have a chance to activate them. I mentioned that this normal form of the reduced dynamics is particularly simple. So normal forms are things we discussed in part 1 of this course. And that theory applies as we applied them to center manifolds. They also apply on spectral submanifolds. There's no particular reason why they wouldn't. They are a general toolkit for simplifying dynamical systems. And especially after you transform the normal form to polar coordinates, or you do the normalization in polar coordinates, then the restricted dynamics on a time-dependent spectral submanifold has an autonomous core, and then you have this whatever phi dot equals, or psi dot, no, that's already psi is included. There's an additional phase here, phi dot omega, which is your frequency in the background. And at leading order, when the forcing is small, and this enables you this scaling, the core of the system, this is the SSM dynamics, right? Because the SSM is now, the total dimension of the SSM is 3, given that you have forcing involved in the game, right? So the SSM is attached to a periodic orbit. So you have to carry that cup around a periodic orbit. The cup is 2-dimensional. When you carry it around the periodic orbit, it's 3-dimensional. But when you use normal forms, then it has the effect of decoupling 2 of those directions, which are basically the radius and the phase along the original SSM from that additional forcing. That's what you see here, that the leading order, this doesn't contain the forcing frequency. It actually does, because this is a phase shift from between the natural motion that you would have on the SSM and the forcing. But we have introduced a new variable that exploited that symmetry, that only what would appear here is only the polar angle of the SSM motion minus the phase associated with the forcing. So if you introduce that as a new variable, as psi, then you have a self-contained system that only depends on rho, which is your distance from the origin, and that phase difference between the forcing and the motion, the polar phase on the SSM. And at leading order, that's a self-contained system from which phi dot equals, say, omega, or whatever, the forcing decouples, and only the unnormalized terms that I did not put in normal form introduce that coupling to this equation, making then this a truly non-autonomous equation on the SSM. But at leading order, you get away just by analyzing this system. And this is a 2-dimensional autonomous system. And what I was telling you is that you can analyze, you can find those periodic responses just by finding fixed points of this system. And if you work on the system, especially, this is some general polynomial function of the polar radius, and this is the rotation speed, nonlinear function, which is at leading order is just the natural frequency of the the SSM itself that you would have. Well, actually, this is the forcing frequency as it is currently. So it's a deviation from that. And plus correction terms. I mean, these have their own. Long story short, you can just analyze this and find zeros algebraically of this right-hand side. So that's an algebraic problem. And you can find all those zeros that I'm showing here in the SSM without ever doing any simulation, just solving for the zeros of that right-hand side. So you can get this whole shape, these, including the isolars, because some of the zero set of this function can be complex. Complex not in the sense of, in the complex of being complicated, right? And you can have isolars as well. So this is sort of an illustration from this paper that you would have a moving spectral submanifold in, which is sliding along several coexisting periodic orbits at this point, at this forcing frequency. One of them can be the basic orbit, which is down here, which is kind of a perturbation of the equilibrium point that you had. But you may have another one, excuse me, this red one here, which would correspond to the lower branch, unstable branch of an isolar. Then you get further outside, you get a third one, which is this one here. So that is the idea behind, this is how you can sort of, in a moving SSM, you can reconstruct basically not only this more trivial geometry, but analyzing the zeros of this right-hand side actually can give you an isolar, which you didn't suspect was there. And you're not finding it numerically by numerical simulation, but you're finding it by analytically, in the sense that you're looking for zeros of this. You may not be able to do that by hand, but for instance, MATLAB has a command that just asks, you can ask for the joint zero level set of these two functions, like that. Joint zero level set. And there's just one command, and MATLAB, to the best of its knowledge, will return all the zeros of this right-hand side, right? So that's being done very efficiently. And just imagine that you may have started out with a system that has 150,000 degrees of freedom, and at the end of the day, the response to predict its response curve comes down to solving for the zeros of a two-dimensional function by one command. And if you say that's a nice story, let me know when you can do that, because I got that response before. And I said, I can't do that now, but maybe I come back and I can do that. And that's what I wanted to show you, that we can do that now. Let me see how the remaining few minutes, I'll just show you a few slides, but that means I have to share my screen from here. So which one? Yeah, this was just a talk that I gave last week, and some of this material was actually coming from UR, who's also in this class. So he's ahead of us already at this part of the material. So that's kind of funny that so he could be teaching this class, right? But then what would I do, right? So I need to support my family. So okay. So this is just a motivation slide of this talk that I gave, is that these complex systems these days, that people look at when they optimize everything, and they look for lightweight structures and they look for efficiency, then these tend to be highly nonlinear, especially in MEMS, but even in aerospace, right? And then if you run this movie here, I mean, you can be sure that the designer of this airplane did not think of this modus operandi as the ideal one, that the wings are oscillating. That's not how it was designed, right? I played once more. That's undesirable. That's a limit cycle oscillation, or a forced oscillation. But that also means that it's a fundamentally nonlinear system, because this airplane can also fly, with quasi straight wings. And then all of a sudden it has a stable limit cycle. So there has stable state, stable limit cycle. There has to be at least one unstable in between. So this is a fundamentally nonlinear system. A linear system cannot produce this. So I'm just saying that because there are efforts now in the model reduction community to approximate everything with linear systems. And that's where the data-driven current reduced order modeling is going. I mean, those are the buzzwords. If you ever hear these, and chances are you will or have, dynamic mode decomposition, various versions thereof, Koopman decomposition, and all this. These are the buzzwords currently. And people use these results and fundamentally are fitting linear systems to nonlinear ones. That can be successful if you choose the right coordinates, because if this is the trajectory of your nonlinear system, a spiral inwards, then if you work well, you can find a linear system in that regime, which will also do this, and its trajectories will be close. And when that's the case, then a linear modal analysis, dynamic mode decomposition will work. But these are prime examples in which you know in advance that it's not going to work, because a linear system cannot have two competing stationary states that are isolated from each other, an equilibrium point in the limit cycle. A linear system doesn't do that. Cannot. And a linear system cannot produce the response, because we've seen, one state, another one, and the third one. So these methods do not have a chance to model this correctly. But these are the types of problems that we face in beam observations. I'm not going to go through this because these, one way or another, you've heard these. This is just the introduction to SSMs and the theorems. And this is the team. Shobit, who's a postdoc of mine, and Mingwu, another one, who's been working on SSM tool, which does this now in arbitrary dimensions, computes these spectral submanifolds for very high dimensional problems very efficiently, if the equations are known. So it's actually an open source package that's available from our webpage, that you can just input your equation here and it will compute everything for you and reduce the models if the equations are known, right? And I just wanted to tell you that this is a wing, and it has 135,000 degrees of freedom. Multiply that by 2, that's 270,000 dimensional dynamical system. And there's nothing that we currently are familiar with that could compute forced response on this. You would have to do direct numerical simulation and wait until, which is very cumbersome for these large dimensional systems. And even then you would only get the stable branches, right? And you would never get the isologs, and if there are. And this is an SSM calculation in which no simulation was performed for 270,000 degrees of freedom, and you get this response curve, including the unstable branch. We're not aware of any other approach that would be able to give you this. And this is simulation free. And depending on what order for approximation you want for the SSM, it can range from 11 minutes. And this was before it was optimized. Now it's optimized, so it's much faster. And this was not parallelized at the time either. So the more you throw more processors at it, then it will be even faster. But it's amazing, given that just to get one data point normally takes, the simulation of that takes longer than this, and you would only get the stable ones. Right? This is another example that Mingwu did, in which the SSM had to be 4-dimensional because there was an internal resonance between the first mode and the second mode. So in that case, you would violate the existence for 2-dimensional SSM. It had to be 4. Again, he shows this is 500,000 dimensional dynamical system, because the degrees of freedom is 240,000. Yeah. And again, that can still, he can do the whole thing within a day. And you say, well, that's kind of slow, right? No, there's no alternative. You cannot, there's no other things we can do at this point. Any other method that would numerical continuation, harmonic balance, and all these things could not do more than 50 degrees of freedom. So not 500,000, right? And even when they approach 50, then they would be 3 days already, okay? Things like that. And, and this is perhaps a little bit to the question that what if you have quasi-periodic forcing? I turned that around. What if you have single harmonic forcing, but it excites 2 modes at the same time? So the response is quasi-periodic. Now, this was the linear response, okay? And you get these complicated response curves because at the same time, 2 modes are activated. For instance, and they can have a Hopf bifurcation. So the periodic orbit may go through a Hopf bifurcation and produce a torus. So he then verified individually by direct numerical simulation these are correct. And what you see here is an invariant 2 torus as a result, which was created from the interaction of these 2 modes, which are in resonance with each other under single harmonic force. So this is in this very high dimensional phase space. It lives within one SSM. We would not be able to compute that torus directly, but within the SSM, which is 4-dimensional, we can use numerical continuation and find it. And this is the work that also UR was involved in. very heavily, and was started by Mattia as a student of mine who's finishing, is that when you do this on data, and then absolutely have no time to go into that, but you can try to reconstruct this in the phase space of delayed observations of a single variable. I didn't talk about that technique in this class, and now I realize I should have. That what if you have just a single observable of a dynamical system, not coordinates and equations? How can you still try to reproduce the dynamical system? And there's this technique of taking delayed images of the same, or images of the same, strobing that variable and building a new phase space from the strobed images. But it's not a Poincare map technique because the signal is not periodic, right? It's called delay embedding as its own theory, right? But you're basically building a new phase space and you're tracking the evolution. You always include kind of a short history of that in the form. One data point there is the current observation, delta t later, and you maybe do that 5, 7, or 10 times. And then that's one data point in that phase space. So that's the delay reconstruction and delay embedding. And then you have a multidimensional dynamical system there, and you can try to reconstruct SSMs from data. And that's what this code does, which has not been released yet, but it's basically in the same form as SSM tool. And maybe I'll just show you that you can have an experiment. These are collaborators from Bremen, and you worked hard on producing from this data that you see here, in particular from the center of mass of the fluid, which they recorded here. This is how the fluid moves. And it's left and right. And its center of mass was a convenient observable for the experimentalists. And this is the data that UR was using, actually just 2 observations of that, 2 trajectories. And this dynamic mode decomposition had a hard time, especially when you include both trajectories. It would not reproduce even the linear system. The response that you get from the experiment seems benign. It doesn't reveal any nonlinearity, because this is just the unforced experiment. And you can imagine what if you do this with a glass of water, right? And then you let it go, then it will go like this for a while and then goes down. And led by that, people think, oh, it's just a linear phenomenon, right? Because it's exponentially decaying signal. See that? It's basically the experiment is this red signal. And there's a lot of nonlinearity there, but you're not exciting it. You're not bringing it out. So what you could do is reconstruct the SSM reduced dynamics for this, and then add forcing already in the model, and then see whether if you do the same experimentally, then your predictions for the nonlinear response match with the experiment or not. So that's the last thing I want to show you, and then I'm done. So here's the reduced order model that you are extracted on the SSM. This is the SSM dynamics in the reconstructed, in the delay embedded phase space, just from 2 trajectories. This is that normal form in polar coordinates, okay? And then you can just add at leading order the forcing without doing that experiment, and solve for the zeros of this as a function of the forcing amplitude, okay? That's purely based in your model, and then make predictions for a family of curves depending on the magnitude of the forcing, and then try to verify that experimentally. And see what you see here, the various continuous curves are just predictions from this little system from which you can explicitly calculate the location of periodic orbits. The 2D autonomous system, you can just do trigonometric magic, square the equation, add them up, and you get explicitly this forced response curve, which is basically use F as a forcing parameter, and you get this family of fixed points. This is what you see here. And what you see on top of that is the actual experimental measurements, which is amazing, because this is then fully predictive. So and even it predicts the phase shifts very accurately. So we're not aware of any other method that can do this. We haven't seen that in the literature, certainly not the dynamic mode decomposition area of that, because it's a truly nonlinear phenomenon, that with coexisting nonlinear states. You do need nonlinear models. If I can have even a 10-dimensional linear model. I can have a 100-dimensional linear model. I can have 1,000 linear, and will not be able to produce this because it cannot have coexisting limit cycles of alternating stability type, right? And it's amazing that 2D SSM can capture that. So I'll just stop there. If you have any questions, I'll take them for today, but you can also ask them tomorrow. Again, I'll be here for consultation. Okay, so I've worn you out. I've worn myself out as well, although for me coffee helps. So that would be the material. I'm finished with that, and if those of you would like to, maybe know a little bit more about any of these aspects, or just have questions about the material, then you're welcome to join me online tomorrow. So I'll be here for a while, and if nobody comes, then I close shop. But as long as people are here, I'm happy to answer any question. Okay. So if I don't see you before the exam, then see you at the exam. If not, then see you tomorrow. And for now, just have a good evening.